so let's begin. We're going to dive into an investigation of a sensory system that, well, it might just be hiding in plain sight. Now, this isn't a story with a nice, neat conclusion. Think of this more as a research briefing, an exploration into whether we've fundamentally misunderstood how some of the most skilled trackers in the animal kingdom actually perceive their world.
We've all heard it, right? The common explanation for why a bloodhound can track someone for miles is that it just has a phenomenally better sense of smell than we do. It's simple, it's intuitive, but what if it's also incomplete? And that's really the core question we need to pull apart, because some key observations just don't seem to fit that clean, simple model.
So here's our roadmap for this briefing. We're going to start by really examining the flaws in that current model. Then we'll propose an alternative mechanism, a different way of thinking about it. We'll look at how its constraints explain real-world behavior, and then we'll map out a framework for maybe replicating it synthetically. And crucially, we'll define how to test it and what would prove it wrong before we end with some notes for the next investigator.
Okay, let's jump right into Section 1, a flawed sensory model. This is where we look at why the idea of just a super sniffer doesn't quite hold up under scrutiny. You know, the accepted idea, the one we all know, is that a dog's sense of smell is just a more sensitive, more powerful version of our own. But here's the thing, this creates a kind of paradox. If tracking is only about detecting airborne scents, why do certain environmental changes, like a bit of water, cause the whole system to just fail completely? That gap, that's where our investigation really begins.
So that leads us to Section 2, where we're going to explore an alternative causal mechanism. The goal here is to try and separate the phenomenon itself, the tracking, from the label we've put on it, the word smell. First, we have to be really precise with our language. What we typically call olfaction or smell is specifically the detection of volatile compounds. These are molecules that easily turn into a gas and just float through the air into our nose. This distinction is absolutely critical for what's coming next. And this slide really lays out the key difference. On one side, you've got olfaction, smell, which deals with volatile gases. But the system we're proposing here, vomeronasal analysis, it detects non-volatile molecules, things that are delivered in fluids or as actual physical particles. So we're not talking about light, evaporative scents anymore. We're talking about heavy biological signals like hormones and proteins, which are detected by a totally different piece of hardware, the vomeronasal organ, or VNN.
So how does an animal get these heavy, non-volatile particles to that special organ? Well, it happens through a very specific observable behavior called the phlegm response. You've probably seen it, a horse curling its lip, or a cat that kind of freezes with its mouth slightly open. They aren't just trying to get a better whiff. They are physically pumping moisture and particles to this secondary processing unit. It's a fantastic illustration of the point. It's an active process of literally tasting the air.
Okay, let's move to Section 3 and see how this all connects. Because if this model is correct, its physical constraints should explain behaviors that the old smell model just can't. So let's look at a classic failure case.
This brings us to what we can call the bloodhound paradox. The process starts, as you see, with a trail of non-volatile particles, skin cells, proteins. The hound uses its VNO to follow this physical trail. But then, look at step 3. Water is introduced. It doesn't just mask a smell, it physically disrupts the medium. It washes the particles away. And here's the crucial point. The information pathway itself is now broken. The hound fails because the data it was processing is literally gone, even if some volatile scents might still be hanging around in the air. And that brings us to Section 4. If we think we understand the biological mechanism, can we actually build it? So here we're going to propose a formal taxonomy, a structured language for a machine-based sensor that could mimic this kind of fluid phase analysis. To build a synthetic sensor, you'd have to start with the absolute basics of survival, right? The system would need to identify these core signals. Is there energy available? That's what sweet tells you. Are there protein building blocks? That's umami. Are essential electrolytes present? Salty. Is something potentially spoiled or unripe? Sour. These are the absolute fundamental building blocks for reading a chemical environment. All right, next, the system needs to be able to detect threats. So this is where danger and spoilage signals would come in. You'd need a bitter class for toxins, a rot or decay class for spoiled proteins, a rancid class for spoiled fats. This isn't just about finding food anymore. It's about assessing the safety and the quality of the surrounding environment. And this is where the concept gets incredibly powerful.
We could design machine-specific classes that go way beyond what nature has evolved for simple survival. Imagine a sensor that can decode hormonal fragments to assess stress, or one that detects exosomal proteins, these tiny packets released by cells, to find the earliest signs of illness. This moves the technology from just tracking an animal to things like proactive medical diagnostics, essentially learning to read the chemical trail of life itself. Now, we get to what is maybe the most important part of any real scientific inquiry. Section 5, Testable Predictions and Boundaries. How would we know if this idea is right? And, maybe more importantly, how would we know if it's wrong? To verify this, we need concrete signals we can actually measure. First, we should be able to physically go out and find and measure these non-volatile protein markers along a known trail. Second, we could monitor an animal's VNO activation and see if it directly correlates with the density of those particles, not the airborne sense. And of course, the ultimate test, building a synthetic sensor that can successfully track using only these fluid phase mechanisms. And here it is. This is the kill switch for the whole hypothesis. It's clean, it's direct. If you could find an animal with a non-functional VNO, but a perfectly good sense of smell, and that animal could still track a trail after it crosses water, well, then our entire premise that the VNO is the critical component here would be falsified. The information would have to be coming from somewhere else. Of course, we have to be really clear about our boundaries here. This model assumes that non-volatile particles are the primary information carriers, and it assumes the VNO is sensitive enough to even detect them at low concentrations. And it's also really important to acknowledge competing ideas. I mean, it's possible that an extremely sensitive nose, combined with an ability to detect tiny physical disturbances like crushed leaves, could also explain the behavior. We have to hold these possibilities in parallel. And finally, Section 6. This isn't a conclusion. Think of it as a handoff. These are the open questions that just naturally arise from this model, notes for the next investigator who decides to pick up this line of inquiry. So what's next? Well, we need to know how long these particle trails actually last in different conditions: sun, rain, wind. Can the VNO's processing power actually separate one trail from another when they cross paths? From an engineering standpoint, what's the minimum amount of data, the lowest particle density, that a synthetic sensor would need to even establish a track? And to me, maybe the most fascinating question of all, how does the brain put it all together? How does it integrate the gas phase data from the nose and the fluid phase data from the VNO to build one single coherent picture of the world? That integration, that's where the next layer of discovery is waiting.